In this video, we're going to go over organometallic compounds, just a simple introduction into this topic. So let's say we have an alkyl halide, 1-bromobutane, and we're going to react it with magnesium. What's going to happen? Well, this process allows us to form something called the grignard reagent, and the magnesium is going to insert itself between the carbon atom and the bromine atom, giving us this compound. So this is butyl-magnesium bromide. Now, the carbon that bears the bromine atom on the left, that carbon is electrophilic. It's less electronegative than bromine. Bromine is more electronegative than carbon, so it bears a partial negative charge. However, once you insert a metal between the carbon and the bromine atom, the carbon becomes nucleophilic. It develops a partial negative charge, whereas bromine has a partial positive charge. Now, these partial charges are based on the electronegativity of the elements involved. So looking at carbon, carbon has an electronegativity value of 2.5. And for magnesium, it's about 1.2. And in the case of bromine, it's 2.8. So because carbon is more electronegative than magnesium, that's why it's partially negative, since it's attached to magnesium. And magnesium is the least electronegative element between these two, so it bears a partial positive charge. Now bromine is more electronegative than magnesium, so it has a partial negative charge. But the grignard reagent has a nucleophilic carbon, and so that's why it does what it does in chemical reactions. Now, it's important to understand that in order to make the grignard reagent, you need to use an ether solvent. And commonly, the ether could be diethyl ether, or it could be THF, tetrahydrofuran. Now, what the ether does, it basically forms a complex with the grignard reagent. And so here's the oxygen atom of diethyl ether, and it surrounds the magnesium atom. So magnesium has the partial positive charge. And so it's attracted to the electronegative oxygen atoms. So the solvent basically complexes or forms a complex with the grignard reagent, thus allowing it to dissolve in this solution. So when dealing with reactions associated with the grignard reagent, or even when preparing it, you want to use an ether as the solvent. Now, it's important to understand that when using the grignard reagent, you want to avoid using basically any type of solvent that is protic, or that has an acidic hydrogen atom. For example, if you put the grignard reagent in water, it's going to react with water. So the nucleophilic carbon atom will act as a base and take the hydrogen atom, forming an alkane. And so basically you're going to destroy the grignard reagent. And then you're going to have your Mg2 plus ion, bromide, and also hydroxide, which will all be dissolved in water if you react the grignard reagent with water. And so any type of acidic compound, the grignard reagent could act as a base and deactivate itself. So let's say if we mix the grignard reagent with an alcohol. It's going to behave as a strong base, deprotonating the alcohol. And so we're going to get an alkoxide in addition to an alkane. So here is the alkoxide ion, which is going to pair up with the magnesium ion and the bromide ion. So we could just write that as OMGBr. Sometimes you may see it like that. Next up, we have organolithium reagents. And let's take an alkyl halide. In this case, let's use butyl chloride, or 1-chlorobutane. And we're going to react it with 2 equivalents of lithium metal. And we're going to do this in the presence of a nonpolar solvent like hexane. And so what we're going to get is basically an organolithium compound plus lithium chloride. So here we have another carbon metal bond. So lithium has a positive charge, or partial positive charge in this case, and carbon, being more electronegative than lithium, has a partial negative charge. So if we analyze the carbon-lithium bond, carbon has an electronegativity value of 2.5, and lithium is about 1.0. So this bond is fairly polar. And you could think of this as a carbanion bonded to a lithium cation, because this reacts as if it were a carbanion. And so it's important to keep that in mind. Now we can prepare organolithium reagents using halides. So let's say if we have bromobenzene and we decide to react it with two equivalents of lithium using pentane or even hexane. So we could turn this into phenolithium, which looks like that. And as a side product, we're going to get lithium bromide. So that's how we can prepare organolithium reagents. Now the next thing we're going to talk about are organocuprates, also known as lithium diorganocopper reagents, sometimes called Gilman reagents. And so let's say if we have an organolithium reagent represented by RLi, and we react it with copper iodide using an ether. We'll use THF as an example. We're going to get the Gilman reagent, R2 copper lithium plus lithium iodide as a side product. And this reaction is a transmetallation reaction. So here we have a carbon lithium bond, and here we have a copper carbon bond, or carbon copper bond. Now a transmetallation reaction will occur if the carbon metal bond can go from more polar to less polar. So carbon has an electronegativity value of 2.5, and lithium is 1.0, but copper is about 1.9. So for this example, the electronegativity difference is 1.5, and here on the right it's 0.6. So the carbon lithium bond is more polar than the carbon copper bond, which is less polar. So as a result, an organolithium reagent is more reactive than a Gilman reagent or a organocuprate reagent. And so whenever you're dealing with organometallic compounds, the ones that are more polar, looking at the carbon metal bond, they tend to be more reactive. And the ones that have a less polar bond, they tend to be less reactive. So what this means is that organolithium reagents are more reactive than grignard reagents, which are more reactive than organocuprate reagents. So let me take this out. So for the grignard reagent, we have a carbon magnesium bond, and magnesium has an EN value of 1.2. So the difference is 1.3. So as you can see, these two, they're close in reactivity, but the organolithium reagent is more reactive than the grignard reagent, which is more reactive than the Gilman reagent. So you can see that the Gilman reagent is a lot less reactive. So let's say if we have this particular organolithium reagent and we decide to react it with copper iodide using THF, then we can get this particular Gilman reagent, and we could use it to displace a halide on a molecule. So let's say if we have bromobenzene. Let's go back to this example. And let's react it with the Gilman reagent. So the net effect of this reaction is that the bromine atom is going to be replaced by only one of the two R groups. So we have two methyl groups here. Only one of them is nucleophilic. And so we're going to replace the bromine atom with just one methyl group. And so it's a good way to make a new carbon-carbon bond. Next up, let's start with one bromobutane. And this time, we're going to react it with an organocopper lithium reagent that has an ethyl group as an R group. So what do you think the product will be? All we need to do is replace the bromine atom with one of the two R groups. So the end result is that we'll get hexane. And so this reaction can help us to basically take one alkyl group and connect it with another. So not only can we use primary alkyl halides, we can also react it with secondary alkyl halides. However, it doesn't really work well with alkyl fluorides. So in this example, I'm going to use a methyl as an R group. So the end result is that we're going to replace the chlorine atom with a methyl group. So this is going to be the product of the reaction. Tertiary alkyl halides don't work well with the Gilman reagent. So that's another thing you need to keep in mind. Now let's say if we're starting with an alkene and we wish to react it with the Gilman reagent. So here we have the cis alkene. So you can see that the two hydrogen atoms are cis with respect to each other. And let's react it with a Gilman reagent that has an ethyl group as an R group. So all we need to do is replace the bromine atom with the R group. And so the two hydrogen atoms will still be cis with respect to each other at the end of this reaction. And so this is a stereospecific reaction. If we started with the cis isomer, we're going to end with the cis isomer. Now let's talk about reactions associated with grignard reagents and organolithium reagents. So here I have cyclohexanone, and I'm going to react it with methyl magnesium bromide in an ether solvent in the first step, followed by H3O+. Now we know that the carbon that's attached to the magnesium atom is nucleophilic, and the carbonyl-carbon is electrophilic. And so when you have a nucleophilic and an electrophilic carbon, these two carbon atoms, they're going to connect, forming a carbon-carbon bond. And so the grignard reagent will attack the carbonyl-carbon from the back, breaking the pi bond. This will produce an alkoxide ion with a methyl group attached to it. Now once we acidify the solution, after the first reaction has been completed, we can get an alcohol. And so the end result for this reaction is a tertiary alcohol. So when using the grignard reagent or an organolithium reagent with an aldehyde or ketone, notice that we can add only one R group. Now let's say if we have an acid chloride or an ester, and we decide to react it with a grignard reagent or, in this case, an organolithium reagent, we can add two R groups instead. Let me add another carbon here. So this is a partially positive carbonyl-carbon, and it's going to be attracted to the nucleophilic methyl group. And so the mechanism is similar to the last example. Here's the first R group that we've added. I'm going to highlight it in red. But in this case, we have a tetrahedral intermediate, which is unstable. It collapses to kick out the chloride leaving group, giving us a ketone. So once we add one R group to an acid chloride or an ester, we can get a ketone. And then the ketone will react with the organolithium reagent one more time. And so this is when we're going to add the second R group. So now we've added a total of 2 R groups, as you can see here. Now the last step is basically add an H3O+. So we need to acidify the solution. And so this is going to give us a tertiary alcohol that looks like this. And so that's how we can react the organolithium reagent with carbonyl compounds. Now let's say if we have an acid chloride and we wish to make these 4 different compounds. So the first one will be an alcohol by the addition of 2 methyl groups, so basically a tertiary alcohol. And the second example will be a primary alcohol by the addition of 2 hydride ions. And for the third example will be an aldehyde. And the last example will be a ketone. So how can we convert an acid chloride into these different compounds? So to make the alcohol by means of the addition of 2 methyl groups, we need to use a reagent that has a nucleophilic methyl group. So we could use the grignard reagent or the organolithium reagent. So we need 2 equivalents of it, followed by H3O+. So that's how we can reduce the acid chloride using a carbon nucleophile. In the next example, we need to reduce it using a hydrogen nucleophile or hydride ion. And so the best reagent for this is lithium aluminum hydride. You could also use sodium borohydride. It could reduce the acid chloride to an alcohol, and then followed by H3O+. Now to convert the acid chloride to an aldehyde, we need to add 1 hydride ion. And we could do so using this reagent, lithium aluminum triterbutoxy hydride. So the 3 OR groups makes this hydride ion less reactive compared to the ones in lithium aluminum hydride. And so this reagent is used to convert acid chlorides to aldehydes. Now, what about converting it to a ketone? The best reagent for this is the Gilman reagent. It will react with acid chlorides, but not with ketones. And so it's going to stop at the ketone level. Lithium triterbutoxy aluminum hydride looks like this. We have an aluminum atom with 3 terbutoxy groups attached to it. And 1 hydride ion. So that's how it looks like if you want to see a picture of it. Starting with an ester, how can we make the following compounds? So how can we convert it into a tertiary alcohol? And what reagent do we need to convert it, let's say, into a primary alcohol? And finally, how can we convert it into an aldehyde? So to add 2 methyl R groups, just like before, we can use a grignard reagent or an organolithium reagent. So let's use 2 equivalents of the organolithium reagent, followed by H3O+. Now, to add 2 hydride ions, we need to use lithium aluminum hydride. We can't use sodium borohydride, that is NaBH4. NaBH4 can reduce aldehydes and ketones and acid chlorides, but it can't reduce esters. It's not strong enough. Esters are less reactive than aldehydes, ketones, and acid chlorides. Now, what about making the aldehyde? In this case, we're going to use something different than the other reagent, lithium, aluminum triterpetoxyhydride. We're going to use something called DIBAH. Sometimes you might see it like this, sometimes you might see it as DIBAH with an H. But it's the same thing. And then in the second step, we're going to react with water. Now this reaction has to be carried out at low temperatures, negative 78 degrees Celsius. You could achieve this temperature by using dry ice. Dry ice sublimes from the solid state to the gaseous state around negative 78 degrees Celsius. And it's useful to use dry ice because the temperature will stay the same until all of the solid sublimes into a gas. Now, DIBAH looks like this. You have an aluminum atom with two isobutyl groups attached to it and one hydrogen atom. And so it's called diisobutyl aluminum hydride. And so I'm going to stop it there for this video. And so I just want to give you a basic introduction into organometallic compounds. There's a lot of other reactions to know, but these are just some of the basics. Thanks for watching.